Hello, welcome to my little math project. I'm here to teach you about radioactive decay slash radioactive growth. We're going to be going over both of them, at least the basics of it. And I apologize, I was going to have a different format, not a slideshow. I was going to have my face and everything, but plans fell apart. So we're going to be doing this instead. But I'll make sure to go through everything that's necessary and much needed when you want to learn about radioactive decay and radioactive growth. But I want to give an example of an application of why you would need to know a little bit about this. Let's say you're in the defense industry of the United States of America. This is very prevalent to, let's say, our nuclear arsenal. Our weapons need to be replaced every so and so years due to radioactive decay because the materials inside slowly, over time, they fall apart and go from a radioactive isotope into a more stable element, which can no longer have the same explosive impact as a nuclear weapon. So that's just one of the many examples that radioactive decay and radioactive growth can be applied into a job, into a career. Anyways, let's get started. So first, the basic formula, your final quantity, which is what you're looking for, is the initial quantity times E, which is a constant that you can typically find in your calculator, depending on what calculator you have, to the power of K times T. Now, K represents a constant. Usually when you're doing a math problem or a chemistry problem, they're going to give you the constant. But in the real world, you might have to find it. It depends how or what you're doing in that career field. And then T represents a time that's usually also given, but sometimes it's not. And we'll get to that. And now at the bottom, you can see the full formula. So QF is going to represent final quantity, and initial quantity is going to be represented by QI. The first example that we got is a fictional radioactive material. So I just made this one here so we can keep the numbers simple and not have deal with big, scary numbers or super small numbers that are very intimidating to read. So a fictional radioactive material has a decay constant of 5. If you start with 400 kilograms of this substance, how much will you have left after 2 days? Round to the thousandths place. Oops, that's a typo. Don't worry about it. So let's take a look and let's dissect this problem. So our K, our constant, it's going to be very clear for this example. It's going to be a constant of 5. Now notice how it says negative 5. And the reason for that is because this is radioactive decay, not radioactive growth. The way how you're going to indicate whether it's radioactive decay or radioactive growth is if the vocabulary of the problem suggests that it is either decreasing or increasing when it comes to the rate of change or the constant. So here you can see it says decay, which insinuates decrease. Now, our time is going to be 2 days. The reason why it's days is because it says it's days. Now, time, it can be days, months, weeks, years, minutes, seconds. It just depends on the problem. So here it says 2 days, so it's going to be 2 days. QI, our initial quantity, is going to be 400 kilograms. Again, the unit of measurement can be whatever. It just depends on the problem. So here it's kilograms, so we're going to use kilograms. Now you put that all together into the formula. You get 400 times E, which is on your calculator, to the power of negative 5 times 2. And then your final quantity is 0.018 kilograms. Again, rounding to the thousandths place. Now let's use a more realistic problem. So these are using real values that you may find in this field if you're in the chemistry field maybe. So iodine 131, which is a radioactive isotope of iodine, has a half-life of 8.06 days according to the CDC. If you have 270 grams of this iodine isotope, how much will you have left after 7 days? Round to the 10th place. So what we're going to do again is we're going to dissect it. So this time we're going to use, you can see, sorry, let me rephrase that. You can see the term half-life. So that is a chemistry term, typically a chemistry term, that suggests decrease. So this is radioactive decay. And it has a half-life of 8.06 days. and 8.06 days is going to be your constant or your K. And since it's decreasing, sorry, it's going to be negative 8.06. Now you're going to do 7 days for your time because that's what the problem says. How much do you have left after 7 days? And then your initial quantity is going to be 270 grams. Put that all together into the formula, you get 270 times e to the power of negative 8.06 times 7. And your final quantity is this very small number. It's very scary looking at it. But if you round it to the 10th place, it'd be like 0.00. So very tiny number. And don't let it intimidate you. Don't let it intimidate you. You'll be fine. Now, let's talk about radioactive growth. We'll skim through this really fast since it's the same thing. It just uses a little different vocabulary. So if you have 200 units of a certain bacteria, if you have 200 units of a certain bacteria grow at a constant of 0.15 per minute, how many bacteria will there be after 30 minutes? Round to the nearest whole number. I will say I did get this directly from the material that my professor gave us. So credit to him or wherever he got it from. Now, let's go to the next slide first. So you can see it says grow, which insinuates an increase. So now we know it's going to be a radioactive growth and not decay. So our constant, which is 0.15, is going to be positive this time instead of negative, since it is growth. Our T is going to be 30 minutes, since that's what the problem says, and our initial quantity is going to be 200 units. Typically, when they say units in any problem, math, science, you don't need to write units at the end of your answer. You could just write the number value, and then that's it. But for the sake of this problem, I am going to add units. So you put that all into the equation, put in your calculator, boom, 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 18,003 units, or you can just put 18,003, unless it has a specific unit that it mentions, like I don't know, grams, kilograms, then you have to use grams or kilograms, blah, blah, blah. Now, in all the other problems, we're trying to find the final quantity, and we've been given time. But sometimes you have the final quantity, but you're looking for the time that it takes to get to that final quantity. And I tried my best to type it out on the slideshow. I could not figure out how to do it. So here's a screenshot of the formula. So it's going to be T equals natural log of final quantity over initial quantity, which you divide all that by the K, which is the constant. Now, we're going to skip the whole word problem thing since to the viewers watching at home, I'm going to have faith in you and I bet you can figure word problems out. So we're just going to go straight to the dissection. So our constant is going to be a very small number, negative 0.0007 years. And our initial is going to be 253 grams. Sorry, our initial quantity is going to be 253 grams. I try to use the proper terms. And then our final quantity is going to be 15 grams. Now, again, I have no idea how to type this out on a Google slideshow. I even tried PowerPoint. It's a pain. So pretend that you're just plugging these things in to the equation on your calculator. You place that all together, put it in a calculator, click enter, click equals, click answer, and you get 403.6 years. This is how you find the time. Now, we know it's years because the constant says years, or maybe the word problem will have just have the word years in it. So that's how you know how to get your measurement of time or your unit of time, sorry, for your answer. Anyways, that is the basics and the gist of radioactive decay and radioactive growth. I hope this has been helpful for you. I hope this gets me an A. And again, I'm really sorry this is a little bit of boring. I wanted to add pictures. I wanted to add all sorts of stuff. I wanted to do a whole video, but plans fell apart. Anyways, thank you so much for listening and have a good one.